Alrighty, so this is a question that we're given in a multiple choice in an exam. We have to solve what this limit is. The limit as h approaches 0 of 1 over h times that integral. Okay, now, as a spoiler alert, I just tried this out on GeoGebra, and now we need to take the limit as h approaches 0. Okay, what this area shows underneath is basically just that integral. Okay, taking pi on 2 plus h and pi on 2 minus h, and that's my h value over here, right? Now, number A, what that means is simply the area, like, the integral, actually, okay? B represents, like, what A over h is. And so when we make h closer and closer to 0, we want to see what B gets closer and closer to. That's what the limit is, right? So if I make B, like, really, really small, right? Making it smaller, right? As h gets closer and closer to 0, it my number or my answer approximates to 1.27. It's roughly 1.27. For larger h's, it deviates away. But for really, really small h's, obviously it's undefined when it's 0. But like when it gets really, really small, we get our answer to be 1.27. But how? I hear you ask. Totally. Because we don't have GeoGebra when we are doing our exam, right? So then how do we get about solving this messy, complicated integral looking thing? Okay, first off, we cannot integrate sine x over x just by using u substitution or integration by parts or partial fractions or whatever we do in 3 unit or 4 unit or 2 unit. Okay, none of these methods of integration will help us solve this sine x over x. Trust me, I tried all of them. So how do we get about this? Okay, so what we do, right, is we gotta take integration at its most fundamental and basic level and relate it to differentiation. This is limits. This is calculus we're talking about. We can relate things together. Okay, what I'm gonna start doing, right, is these are both very weird integrals, because if I just substitute h is equal to 0, I just get 1 over 0 times the integral at pi over 2, and then sine x over x dx, and then that's just 0, and so I just get 0 over 0, which is nonsense, like actual nonsense. This doesn't get me a solid answer, and that is clearly not gonna get me something like a 1.27. Okay, but we're talking about limits, we're talking about calculus, we're 4-unit kids here, right? We got this. Okay, so what we do is, what I can do first is to make this a little bit neater for me. Okay, what I'm going to do is actually take that out. I'm just going to worry about the integral bit, this little bit, okay, and I'm going to work with it, okay, and then I'm going to add these guys in later on. Yeah, okay, so first I can split this integral up. So I can have pi on 2 plus h, and then you have pi on 2 minus h, and then sine x on x dx. Okay, and I can split this up this way, so such that I have the integral between pi on 2 and pi on 2 plus h. Not plus, sorry, that's a minus. So I'm using that definite integration. Not 2. What am I even drawing? Okay, that's a h, yeah. Okay, and sine x on x, and then I have, oh wait, there's a dx there, right? I forgot that guy. And then I have, up on the top, I have this bound, so pi on 2 plus h, and then I have pi on 2. And then the same function, sine x on x dx. Okay, and this is just one of our definite integration rules. Imagine if I have, like, the integral between a and b, okay, of f of x dx. Okay, that's just the same thing as the integral between a and c, f of x dx, x thingo, plus the integral between c and b of f of x dx. Okay, what this just tells me is if I have my function, and this is my little function, okay, and this is my a, this is my b, right, I can pick some value of c, and so the total area between a and b is just the area between a and c, plus, this is my c, plus the area between c and b. And so that's just your total area. We're just applying the same thing here. Imagine if this is pi on 2 minus h, and this is pi on 2 plus h, and this is a specific number pi on 2. That's clearly between pi on 2 minus h and pi on 2 plus h, okay? And you see soon why I'm picking pi on 2 specifically. Okay, now, what I'm going to do is I'm going to let an integral exist, okay? I'm just going to say that if I integrate just the normal integral, the indefinite one, of sine x on x dx, okay, I'm going to say that this guy has some solution. I don't know what function this is, and I may never know, okay? But this is beyond the scope of the syllabus, or the course, right? I'm just going to say that there is some solution, okay? And I'm going to call this solution f of x. Yeah? And so that is just my result, okay? What this means is if I differentiate f of x, that's just the opposite, right? Then I just get f, and I can say it in dash form. F dash of x is just sine x on x. Nothing fancy, yeah? So that these two are just interchangeable, right? Because if I integrate this, I just get this guy, and if I differentiate this, I just get back to this guy. Okay, I'm just going to say that this has some solution, okay? I don't know what the solution is, just reiterating that, yeah? Okay, what I can do with this, right, is I can work it around this integral, okay? What I'm going to say is, from this guy up on top, okay, I'm going to say, well, actually, I'll just equate these two anyway. Pi on 2 plus h, pi on 2 minus h, sine x on x dx is equal to this guy, right? And just rewrite that again. 2 pi on 2 minus h, and then the same guy, right? Sine x on x dx, right? Okay. What I'll do instead, right? This guy, actually, screw it. I'll just keep writing pi on 2 h. I'm way more bothered than I should be. On x dx. Okay, never mind then. Okay, what I'm going to say is, because I assume that there is some solution, right? I can just use the normal definite integration rule, right? Say if I'm, for example, if I'm integrating like between 0 and 1 of, I don't know, 2x dx, right? That's just now, I just do the indefinite integral, that's just x squared, and then I sub in values of 0 and 1, right? So in this case, we agreed that the indefinite integral is just some f of x, and then you sub in the two values, which is just, in this case, 1 squared minus 0 squared. In some other example, right? This is irrelevant, okay? I'm just giving you an example. This is how definite integration works, right? So I'll just get rid of that for now. Bye-bye, go away. Okay, yeah. What I'm going to do with this guy first, okay, is that this would be equal to f of pi on 2 minus f of pi on 2 minus h. Nothing fancy, right? Because we just, remember that we said that the integral of sine x on x dx is f of x. That's what we let it to be, right? You can say let. Yeah? Now, I just subbed in the values, and that's about it. And that's literally what definite integration does, right? Okay? Now, this is just what the integration itself part. I haven't taken the limit at all, okay? Let's take the limit of the entire thing, right? Actually, I haven't finished this. This was only the left part. The right part is just plus f of x on, is it x on 2? No. It's f of pi on 2 plus h minus f of pi on 2. Okay, and you can sort of see why this original rule works, because you see this guy and this guy, they cancel out. So then you're just left with the original integral thing coming out. That's just a side note. Anyway, the point is, we got this guy, and this guy is really important to us. I'll let you know soon. Okay, now if I took the limit of h approaches 0 of 1 over h times the same old integral that we got over here, right? Okay, pi on 2 minus h, pi on 2 plus h, sine x, x on x, dx. Okay, we got this guy, right? Okay. Now, I remember this integral part, okay, I evaluated to be this part, this whole thing, okay? What I'm going to do is I'm just going to put that on both sides in some sense. So I have the limit as h approaches 0, okay? This guy is equal to the integral part, okay? So that's the limit h approaches 0 of 1 over h, okay, of all of this. That guy comes down here. Yeah? Okay. Now I'm starting to be a little lazy. Okay, now what I'm going to do is I'm going to distribute this 1 over h in a very interesting way. Limit as h approaches 0 of, okay, f of pi over 2 minus f of pi on 2 minus h, all on h, plus f of pi on 2 plus h minus f of pi on 2, all on h. Okay? Now, let's just look at this part for now, just for now, yeah? Okay? This, if I'm taking the limit as h approaches 0 of all of this looks oddly like something we've met before. This looks like the differentiation of first principles. First principles. Okay? Remember, just as a recap, right? If I have f dash of x, that's just the same thing as a limit as h approaches 0 of f of x minus h, x plus h, sorry, minus f of x, all over h. Okay, and that's my first principles. That's literally the formula, and that's on your formula sheet. You can straight up look that up. Yeah? So now if I'm just working this into this, right? That means this part looks almost like this, but in this case, x is equal to pi on 2. You can sort of see the relationship, okay? So then that means this whole thing, okay, at least this part, right? Okay, I'm just going to bring that over all the way across and down here. Come on, man, don't run out on me. Yes, okay. And so that's just a lim h approaches 0 of this guy's still there, f of pi on 2 minus f of pi on 2 minus h, all on h, okay, plus, now if I'm just working backwards now, this is just capital F dash, and you have pi on 2. Remember, x in this case is pi on 2. Yeah, and so this makes perfect sense this way. Yeah. So that's that part done, but this part's a little bit weirder now. What if I was working here, right? And if I have, what if I made x, if I changed the x into an x minus h, what happens now? F dash of x minus h is equal to the limit h approaches 0. That's not going to change. This bottom part with the h is also not going to change. But this part, then I have f of x minus h, right? Remember, if I had an x, it becomes x plus h. I just added h to it. X minus h, if I add a h to that, that's just x. And then I have minus f of x minus h. Nothing's actually changed, has it, now, right? Now that's going to look oddly like what we had up above there. This time x is equal to pi on 2. So then I can substitute now that this is equal to the limit, h is still getting closer to 0, of f come on, load, yeah, f dash of, come on, load properly, okay, x, no, it's not x, it's pi on 2, sorry, work properly, please, okay, better, no, it's not better, load, old computers these days, please load, okay, never mind, okay, yes, okay, f of pi on 2, right, minus h, because now x is just pi on 2 in this way, looking and matching, okay, plus f dash of pi on 2. Sorry, it's a little messy, but yeah. I can make these square brackets to make it a little more clear to you. Okay, and so this is just the same integral that we're working up above, right? Okay, now this guy, this boy here, okay, now we can approach, we can make lim h approaches 0, right? And then I just get two groups of f dash pi on 2. Yeah, because when h approaches 0, then this just gets f dash of pi on 2 plus f dash pi on 2, right? And that's just two groups of the same thing. So then I just have two groups, come on, two groups, my weird mouse writing, come on, work, please work, come on, okay, oh, finally worked, okay, two groups of f dash of pi on 2, right? What it means is you're just taking f dash of x, and then you evaluate it at pi on 2. That's what all of these mean. So then, now, how do we figure out what capital F dash is? Wait a minute. We had this rule that we said before. If f of x is defined as the integral of sine of x, then f dash x is just sine x on x. So now I can substitute that in. I have equals two groups of sine x on x. Okay, but x is equal to pi on 2. So I'm just going to write like a weird bracket thingy, and I would say x is equal to pi on 2. So I'm just going to substitute that in, right? So that's just two groups of sine of pi on 2 over pi on 2, right? And now what I can do is sine of pi on 2 is always 1. So that's 1, okay? And then there's a 2 times all of this, and then there's a pi on 2 on the bottom, which is just 2 times. Now, if I 1 over pi on 2, that's just the same thing as 2 over pi. And so this is 4 over pi. Simplifies out, okay? And this is the exact number, right? And if you like approximate this or just type it up on your calculator, this is approximately 1.27, which exactly matches what we said over here, right? As my h gets smaller and smaller, right, my b starts approaching 1.27, which is roughly 4 on pi. That's it.